And because Sarah said, I'm afraid to take instruction from Siri in your book.
Yep. So let's start. So before making some announcements, so the TT contest winners are this one. So feel free to grab one of these. This is the prize. Yeah, feel free to have that. And also, did everyone get the midterm back, right? Yeah, okay, good. And I'll make some announcements. The final exam. So it'll be 2:45 to 4:45 on May 8th, and location will be announced. And then it'll be cumulative, and bring your calculator or your phone. Cheat sheet will be allowed, but there is no cheat sheet contest this time because there's no time to give you those words, I guess. So anyways, any questions about the final before? Yep.
What are the cheat sheet like double-sided?
Oh, one-sided, just like the last time.
No.
Yeah. It should be handwritten and one-sided, just like the last time. Yeah, it can be hard to cram all the things.
You still have to handwrite it?
Yeah. It's a lot, yeah, but
So.
and there will be an extra session for mediation analysis on May 1st. Again, this is an extra session, so it's not required to show. You're not required to show up, but I think it's helpful because it'll be mostly about the problem set questions rather than more full-on reviews. So, yeah.
So we are going to be required to know the information presented in here, even though it's at a time that is very much not the regular scheduled class time, and maybe we have work.
Oh no. So the extra session will be just about problem set questions. So yeah. So it'll be let's solve the problem set questions together rather than just present new information that you did not learn or something. So yeah. So I tailored that the take extra session specifically to the time limitation that you have. So and then it'll be recorded via YouTube as well. And then for the attendance, so you'll get an email when you were absent more than 4 times. I think it's only efficient because there won't be any impact on the grade if you're not absent more than 4 times anyways. So if you don't get an email, you're fine with the absent and then the attendance score. So but of course, if you want to know your attendance records, feel free to email me so I can just tell you that by email. Does that make sense? But if you were absent more than 4 times, I'll just simply let you know that that you were the record says that you were absent more than 4 times. So if there is a correction needed, you can talk to me about it. Good. All right, the midterm. The midterm results are the mean is 83.7% and the median is 86.7%. And I'll review some of the questions in the midterm now. But before starting that, is there any questions about the grading of midterm 2.
What is the median score?
Oh, what? Mean score? Yeah. Nope. All right. We showed up a little late. Feel free to show up the have the snacks right there. So there is a question 2 in the mechanical and thought questions section. So the question A was asking, considering Z as a candidate instrumental variable, use Phi-Cap rules, and so it'll be covariance between Z and Y divided by covariance between Z and T, right? So AB divided by A, so the answer is B. And the question B was about using P as the candidate instrumental variable. And therefore, you would have that as a result, as the answer, right? This should be pretty okay, right? But the question is, the difficult one was question C, actually. So the question C says, a researcher claims that a valid instrumental variable must not cause the outcome directly, but B must cause the outcome indirectly. Do you agree with this? The answer is no, because I'll explain the reason with the 2 assumptions first. 2 assumptions of IV. The first one is relevance. Covariance between Z and T is not 0, and exclusion is covariance between T and EY means 0. Right? A lot of you answered that this part B speaks to the relevance assumption, right? But this is not quite right, because I'll explain explain this part as well. But even not caring about this part, it must cause the treatment indirect treatment. It should be this should be treatment if it should speak to relevance. Does that make sense? The relevance assumption here does not assume anything about the relationship between T and Y, actually. So it only assumes the covariance between Z and Y, Z and T, and it does not anything to contribute to Z's causation on Y. Relevance assumption is not about that. Does that make sense? So, what? So, the question, a lot of you said this part is actually speaks to relevance assumption, right? But this is not correct. If it would have been correct if this part said the treatment. But it does not say that in the question. Good, yeah.
So theoretically, P does not have to be be connected at all to Y, like
So-
to the outcome, because it's not about the outcome, it's about, for relevance, it's about
Yeah.
P being relevant to T and not to Y. Is that
So
correct? Is that what you're saying?
for the relevance assumption,
Yes.
for the relevance assumption, it would be correct. But in the question, what the question is saying here is they're in conjunction with each other. They speak to the exclusion assumption only, not relevance. Okay? They're speaking to exclusion assumption. And what's wrong here is that, so I explained why this is not really related to relevance assumption, right? So that's out of the window. So even with the exclusion assumption, it should be really be associated with. It does not say anything with the cause. The assumption only is saying, speaking to the covariance between T and EY. Does that make sense? Nope.
I just think it's a really badly written question,
Okay.
because it comes in this whole problem of setting us up to answer this question based on the part A and B that we answered before.
Uh-huh.
So it really just kind of threw me off.
So actually the example,
And it made me think that what we have done in A and B were relevant to answering these questions, and they're not.
yeah, so the answer, the B here is relevant to the answer of question C because it is an example of this statement why P does not necessarily have to cause the outcome directly.
The second
Good.
part. It's okay, I just think it's a really badly written question.
Okay, sure.
Overall.
So according to as the question B suggests, it should be really be associated with rather than the cause, the word cause. Right. And the in the short answers, question 8, it has EA, B1, PA, B2, PSCS, and E1. We're talking about short answers, question 8. In question B, what would measurement error in PA affect slope estimate on SES, data 2? Right? So verbally, it would mean that measurement error means that there are still remaining variance in the latent, unmeasured PA, parental aspirations. There would be still, there would be some unmeasured latent parental aspirations. And that can confound the relationship between PS and SES and the outcome. What? Okay. Yeah, I'll graphically explain what's going on here. So PA, latent variable, right? And that affects the measured one. And there will be some measurement error, right? And then it would affect the EA, the outcome, and PSCS, right there. If parental aspirations affect the parental SES, for example, let's say we have these parents have higher aspirations for their kids, so they pick up on more work and stuff like that. And they have higher incomes and et cetera, so their SES increases. Good. If so, even if you control for PA, the measured parental aspirations to get the beta 2 hat right there, beta 2 hat right there, right? There will be some confounders going on. There will be some confounders in the relationship between PSES, PSES, and EA. Good. And that's why that's how measurement error in PA can affect the beta 2 hat. Good. Any questions? Nope. All right. Let's move on. So let's review the last lectures. The first one is fixed effects models. The motivation of fixed effects model is controlling out time constant unobserved confounders or group level confounders. It is mathematically equivalent to adding individual dummies for beta coefficients or slope coefficients. For standard errors, it could be a little bit different, which I'll demonstrate in a minute in the state exercise. So what it's doing here is basically you control out all the time constant unobserved confounders to be more confident about your causality like this. And the most important assumption behind fixed effects is strict exogeneity assumption, which means that treatment should not be affected by pre-treatment outcome or post-treatment outcome. So, for example, fatherhood premium using fixed effects, it can be leading, the models fixed effects used to estimate fatherhood premium can lead to a bias because of the possible violation of strict exogeneity, meaning that you could earn some more money because of your marriage or parenthood, but you can get married or have children because you earn more money. There's reverse causality, right? Does that make sense? So it is always a possible alternative explanation, right? So you're assuming that there is no reverse causality, meaning that you don't earn, you don't get married or have more children because you earn more. You're assuming that out, excluding that possibility out by assumption. Does that make sense? Any questions about the strict exogeneity assumption? All right. So, and then we also covered MLE and panel models. So, panel models are simply an HLM with panel data, really. And so the motivation here is basically this is firm 2 and this is firm 1. And firm 2 has higher errors, positive errors on average. Positive errors on average because they have higher means even after regressions. And they have lower mean, so that's why they have generally negative errors or negative errors on average, right? So these intercept differences or something, a set of unobserved characteristics of that firm leads to correlated errors. In other words, there's something going on with the firm that is not explained by the regression model that affects the intercepts differences. That affects intercepts, right? And that's why these errors are correlated with each other. They're generally positive. They're positively correlated with each other. Positive. Does that make sense? Good. Any questions? So I didn't mention that in the lecture per se because I didn't want to confuse you. But to be really exact, these two errors are numbers, right? Which means that they don't have any covariance or correlation. But it really means that if you sample multiple times, you would have that. And then you can calculate the covariance, right? And then they would be positive. These covariance would be positive. That's what it means. Yeah.
So that they don't have, the errors don't correlate.
They are correlated with each other.
Okay.
But to be exact, like you have only one sample in your data, right? Only one sample in your data, right? So these two error amounts are numbers. Two numbers don't have any covariance, right? Does that make sense?
Okay.
But what it really means by correlated errors is that if you multiple infinite times, then you would have these dots for the first observation of that firm 1. First observation or the first firm's observation at time t, which is a little bit hard to change your mind about, like translate your mind into a theoretical realm. But if you if you sample infinite times, then you would have these observations, and then you would have these observations, and you would have these observations. And you look at the correlation among these errors. Does that make sense? Sort of?
I can stare at it, it's good.
Okay. This is more of a technical clarification. Okay. And then, so that motivates the HLM models for panel data or panel models. And then as we saw that there's something going on with the group or panel that really leads to correlated errors. If so, does it affect beta 0 I? This is set of unobserved covariance that affect y, right? And therefore, they have higher intercepts, and that's what it's called. That's what's causing correlations among errors, right? And what fixed effects model does control for all these intercept differences for the possibility of being a confounder. What if these group level or panel level characteristics that are not observed are also affecting the x variable as well? So to be able to exclude that possibility, you are controlling for all intercepts, panel intercepts.
Pattern means like longitude.
Panel means each unit, a firm for an individual that is followed up across time, etc., etc.
So there, yeah, full vertical wise, so what? What's the meaning? So what's the meaning of full vertical wise using that firm too?
So they mean that the error levels are positive on average compared to form 1. As you can see right there, the errors are generally negative in form 1. And that's because the group intercepts are different. Okay? And that's why the errors are correlated with each other. Okay? You can expect each other. That's what correlation is. Right? One is negative and the other is negative, or etc. And obviously, this is an advantage. This is an advantage of fixed effects models, but it really means that you have to control for all the intercepts, right? Panel-specific intercepts, right? And that means that you are using a lot of degrees of freedom to estimate all the panel-specific differences. So that's why it's inefficient compared to random effects models. But for random effects models, it is as long as you can assume that is a set of unobserved characteristics or panel-specific unobserved characteristic do not affect XIT, then you don't have to control for it. If so, you can have more efficiency in random effects models.
I'm sorry, could you restate one more time why the fixed effects model is less efficient than the random effects?
So you are estimating all the panel-specific differences from the grand mean, right? You are fixing them, right? So you are, say, it's same as like adding all the panel-specific dummy variables. So if there are 500 panels, then you are adding 499 dummy variables, right? It means that you have to estimate all these different things, and then you are using up all the data for the estimation. So it means that you're using a lot of degrees of freedom, and that leads to the efficiency inefficiency of fixing it. Does that make sense? Yeah, so you are estimating all of the, you're fixing a lot of data points, and then to be able to get the same level of precise estimates, you have to gain more sample size.
So what's the difference between HLM and HLM's panel?
HLM, so panel models are simply HLM, but it is just for panel data. So the time points are nested within panels. So the panels are groups, and time points are like individuals in the group.
So I longitudinal follow a curve over time.
T1, T2, 3, 4, 5, and then panel 1 is down. So these time points are nested within the panel.
So panel is from one.
Yeah. Exactly. So it's basically same as family 1, there are 5 children. It's same as that. Okay. All right, let's cover data exercise. Download the, go to the course website, and then there will be a panel practice folder. There will be another folder called LGCM. This is about latent curve, growth curve model. Latent growth curve models, which is optional. So I won't cover that in the section today. But if you have any questions about it, I'm happy to answer. But what we're going to focus here is the panel practice 2.5. Let's change the directory right there, and let's look at the data. As you can see right there in the data, what we're doing here is I'll tell you the basic setting first. The basic setting here is the look at the gender's effect on depression scale, right? So the depress is the outcome right there, and female variable is the independent variable of interest, and then there are other control variables, the number of close friends, and the satisfaction with the family life. And then as you can see, this has the structure of panel data where IB variable, the same person, 14201, the same person is followed up from wave 1 to wave 3. The same person is measured repeatedly by 3 times. All right? Any questions so far? Nope. All right. So yeah, this is basically cooked data. I cooked some data on adults' depression level. So as I was saying, the panel data are also called cross-sectional time series data because it has sometimes cross-sectional features, right? You have more than one unit in the data. That's why it's called cross-sectional data. But also, it has time series features as well. The same units are followed across times, right? So that's why panel data are also called cross-sectional time series data. Any questions?
So what's the meaning of cross-section?
Cross-sectional means that there is more than one unit in the data. So multiple people are involved in the data. Multiple people are responded to the data. It's a special case of nested data because timed data points are nested within each panel. So the group here is each panel or a person, and time points are nested within the panels. But it's a special case because it has some implications in causality. Because past cannot be affected by the future or something like that. So with that in mind, it's a special case, but we don't really cover how they are different, how it can be a special case. But it is let's just note that this is a special case. All right. And we're thinking that it's just an HL in this class. Any questions? Am I making any sense? Sure, yeah. So appropriate modeling is needed because it might lead to clustered errors, as I was saying. So that's why we want to use HLM approaches to model the causal effect of gender on depression level. There are some classification schemes of panel data. The first one is balanced versus unbalanced. Balanced panel data mean that everyone has the same length as the time period. So in this case, everyone answered all of the 3 weeks in the data. If so, we would have balanced data. But in the real data, we saw right there are people who did not answer to the questions in wave 2 or wave 3, actually. They just dropped out of the panel. Okay. If so, we would have unbalanced panel because not all people have the same length as the panel time period. And then the second part of that classification will be whether you have time gaps in panels. Time gaps between panels. So, for example, some people, this is not the case in our data, but some people choose to answer wave 1 and wave 3, but not wave 2. If so, there is a time gap. Right? This is an issue to think about, but in our example, we don't really have that. So let's just ignore that feature for panel models for now. Good. Any questions? Nope. All right. Before starting again, let's take 5 and come back.
So great.
It's because we all won the cheat sheet challenge. We have
Everyone won. I won it.
oh my gosh.
So nice.
No, no.
Oh.
Who's the I wasn't here. Okay, wait, did you know?
Yeah. Because I was in response to them.
Oh, yeah. That makes you like, I heard how actually went on Friday. Okay, he actually had it. We have places. But, yeah, so I didn't really bring this up. I asked, we said, are there things like under residence yet? And then we finished our Friday. And then we run outside and we said. Actually, I don't have it. Did they put you in handcuffs? No. Oh. That's why I love it. Yeah, I missed all the questions. Yeah. But, the team, Oh, let's go back here and people behind us. Oh. Yeah, that's fine. We forgot. Yeah, no, that. Why, like, I thought my brain, like, don't think about. Like, that was. Yeah, there.
Alright, let's start the session again. Sure. Oh, so they should be separated. Oh, sure. Yeah.
Yes.
Alright, let's start. So the first thing you should do to analyze the panel data is to XT setting the data. So it's basically declaring the data as a panel data set. So the command here is XT set ID weight. You should put the panel ID first and the weight here you go, later. Good. And then if you type XT desk, you would have that output. The number of panels is 2,002 something, 200 something. And even though the observation numbers are 6,000, right? Meaning that the same individuals are measured repeatedly. Good. And the T here is 3 because the number of waves is 3. So the individuals are measured by 3 times, or the variables are measured by 3 times. And then this distribution of Ti suggests that there is a person or there are people who answered only one of the waves, but a lot of the respondents answered all of the 3 waves. All right. Good. Any questions? Nope. All right. And then there is a pattern right there that shows the patterns of answers. The first one is you answered all of these in all of the waves, and a little over 2,000 people answered in all of the waves, and 151 people answered in wave 1 and wave 2, but not in wave 3. Good, etc. And then if you type xtsum command with the variables names, you would have that. So the number of observations is 6,509, but the panels numbers is the number of panels is 2,248, and the T bar is 2.89, which really suggests that almost everyone answered in all of the waves, because it's close to 3. It shows the average of length of the time series. Good. Any questions? Nope. All right. And the overall part is the summary of the variable without regarding any of the panel data structure. It's just a summary of the variable. Okay. Does that make sense? And the between summary here is after you aggregate all the data by panel, you get the minimum and maximum. So for example, there is a person who has 1 as the average of all the time points. Does that make sense? As a depression level scale. So this person would have 1 when they had 1, 1, 1 as the depression scales for all waves. And then you average them out, and then you would have 1, right? And then for 4, this person answered 4, 4, 4. And then if you average them out, then you would have 4. They are all standard deviation, minimum, maximum, and they are all about the data after you aggregate the panel data by panels. Does that make sense?
So the between and within.
I'll explain that. you aggregate the data to this one. That's what I mean by the aggregation of data by panels, right? And then within this row means that after you subtract all the panel specific averages, what would be the minimum value of that? And what would be the maximum value of that data? So for example, you would have that, right? And then you are summarizing this variable. And then that's the maximum value, minimum value, maximum value, and standard deviation you will have. Good. You can see other variables according to, you can interpret the other results as well. And if you type XD tab female table, and you will see overall table that is not regarding any of the panel data structure, right? And for between, you are saying that there are 1,141 male panels in the data and 1,107 female panels in the data. And within percent are all 100% because the panel data happen to have no variance in the shift in the gender identification over time within that panels. So there is no person who said, I'm a man in the wave 1, and then they shifted their gender identification in wave 2 or wave 3. There's no case in that data. Good. And more specifically, you can see XD trends. So it really shows the transition of certain categorical variables. You started from females of 0 in the wave 1, and then in the wave 3 you ended up with a 0. All of the data are looking like that. And if you started from 1 and you ended up with 1 in wave 3. So again, there happens to be no change in the female variable across time within the panel data. Obviously, it is associated with the measurement issues of the gender identification, but this is the limitation of the data. And you see that if you type XT line, you press data, but with the 9 people right there, then you can see how individuals change over time in terms of the depression scale. For the first person, this person was up there in the depression scale, it decreased a bit, and it increased a bit later. And et cetera, for other things. And the option overlay actually makes it possible to combine all the trends into one graph. Without that option, you will have different panels in the graph. And after installing the XD graph package, you will have XD package depress. This it shows you the depression scales average across time. So for all panels at time 1 had 1.95 as the depression scale on average, right? And then it went up to 2 and went down. Does that make sense? So this part is, this number is basically all panels average in the depression scale at time 3. Good. And let's run the pooled OLS state model, which means that you are just running on OLS regression without regarding any panel data structure, right? Meaning that you're assuming that all the observations or all the errors are independent to each other. You're not really thinking about correlation, possible correlation among errors. You're not thinking about it. Good. And as you can see, the number of observations is 6,000 something. And female variable is significant, positively. Close friends is positively negative significant, and fam satisfaction is negatively insignificant. The problem here will be correlation among errors, right? Because of panel intercepts differences. There could be other sources of correlation among errors, for sure. But one of the sources could be panel-specific intercept differences. Good. And if you run the same command with a mixed package or command with the ID variables and run the stat ICC, it shows you that how much of panel-specific intercepts are contributing to the outcome level. Does that make sense? How within chain, like so how panel-specific intercepts, they are how much different in outcome compared to total variance. Good. 44% or 45% almost of the total variation can be explained by panel-specific intercepts differences. Does that make sense? That's what we learned in the HLM part, right? So it means that, it really means that you need an HLM model to deal with these issues. More specifically, because there are panel-specific intercepts, vast panel-specific intercept differences, it is most likely that you have correlated errors, and therefore you have biased standard errors. So that's why you want to use an HLM for panel data. Good. Any questions so far? Am I making any sense or? Okay, good. And let's look at panel models. So let's estimate between effects model first. Between effects model basically aggregate all the variables by panel, right? Like that on the board, right? And then run the OLS regression with the aggregated data. Okay. And the command is xtreg, and you should add BE as an option. as you can see right there, the number of observations is 6,500 something, but the number of panels is 2,200 something, right? And then there are people who have 3 time periods, or there are people who have just 1 time period in the data. Right? And then if you look at the coefficient, female, it should be really interpreted as compared to a male panel, a female panel being a female panel is associated with the 0.133 units increase in the depression scale. Good. Does that make sense? So the panel here is the focus, right? Because between effects model focus on between variance, which is panel averages differences, not variation within panel across time. You're disregarding all of these differences within a panel by aggregating the data or disregarding any within variance. Good. So the interpretation should be done according to that insight. And then there is a complicated formula for within R squared, between R squared, and overall R squared. They are all FYI thing, and you don't really have to know that for the problem set or the exam, but I'll just explain them in case you want to use these panel models for your master's thesis. Right? So, within R squared really means that how much of outcome is explained by the within variance of panels. So, for example, family satisfaction can change over time. And how much of that variance across time contributes to the explanation of outcomes variance. Good. Yep.
Are they too different from ICC?
So ICC is if there is no covariate or there's one variable. So it's more of a rho means like R, correlation coefficient actually. So if you square it, then it looks like this one, like in the nope. They should be same. Sorry. They should be same when it's only one variable in the model. But in real life, like you don't really have that. And the rho here, I mean like within, right? In the between effects models, right? Because so to be really clear about that, let's just not connect between the two. But rho is basically how much unexplained variance of at the group level is coming from the how much of total unexplained variance is coming from group level unexplained variance. That's what rho says. ICC says, sorry. But R squared is about how much you explain of y with that with invariance, if that makes sense. So in a way, it's a reverse relationship about, especially about between R squared, actually. So if you divide this one and yeah. So between R squared is about how much panel intercept differences are, or panel average differences are explaining the outcome. And overall, it's just R squared. And then this is actually can be clarified if you compare the results with the OLS with aggregated data. Let's see that. So, instead of using XTReg, I am manually aggregating the data. So the first command is preserve, which is preserving all of this, the data. So everything you can do can be revert back after you have restore command. So any modifications you did in right there will be reverted back after you type enter the restore command. Okay. This is not really important. What's important here is collapse command. Collapse means you are collapsing all of the variables in terms of the average of them by ID. So what it's doing right there is precisely this aggregation. You're collapsing the variables, collapsing the depressed variables into this one, the mean. Does that make sense? So that's what that's how the aggregation works in the Stata. And then you run the OLS regression after that.
What was the meaning of 18 parentheses?
This one?
Yeah.
This one is the sample you used in the previous estimation, right here. Right? The samples you have used in the previous estimation. So to compare the models, right? We're trying to compare the two models, right? And so to compare the two models, we have to use the same samples, right? So that's why we added if the sample one.
So what means?
What means you have used these samples from the previous estimation. So does that make sense? Yep. All right. And then, as you can see, coefficient and standard errors will be exactly the same because they're the same models. Okay. And the R squared 0.448 right there is same as between R squared and the between model. And then this one, this complicated looking part is same as the root MSE in the aggregated OLS regression model, which really means that how much the level of unexplained variance in panel level intercepts. Panel specific intercepts. How much the square root of the variance of the panel specific intercepts. Does that make sense? So there would be like, after you explain these between level differences, panel specific intercept differences, right? After you explain some stuff out, some of the variance out, you still have intercept differences, right? And then you are, and that's what it means by that. That's why it is same as the root MSE in the regular aggregated OLS regression. Any questions?
Can you say that again?
Sure. Sure. So this is same at that one. That one is SC of UIs, right? Meaning that you have each errors with after aggregation, right? After aggregation, you run the OLS regression, right? With that data, right? And then after that, there would be some errors, right? And then this could be called U1 hat, the errors in the data, the errors after the regression. U1, U2 hat, U3 hat, etc. And then you are summing all of the UI hats squared. And then you square root. And that's root MSE in the aggregated OLS regression model. Good. But that's all. Again, that's the last thing I want to mention is the F statistic, which is 35. And here you can see the F statistic is also 35 as well, because they are the same models. All right. So again, these are squared, and this ST of standard deviation of UIs, these parts are not an F statistic, all that, they're not covered in the midterm or the final or the problem sets, right? They're not necessary, but this is just FYI, in case if you interested in running panel models for your masters. Okay, let's look at fixed effects models then. So fixed effects models is about the effects coming from within variance, right? What does it mean then? It means that after you subtract all the panel-specific averages and then look at how the depression level changes over time, right? Within that panel, after you subtract the panel-specific mean, right? And then you do the same thing with the other variables, and then run the OLS regression. That's what it means by you're looking at within variance. Good. Any questions? Nope. So let's look at the results. The the command is same, but the option here is now FE, fixed difference. And the biggest difference here is that the female variable is now omitted. Why is that? Why is the female variable omitted?
Oh, this is something like that. That was a good thought. In my mind, as we go.
Anyone? Anyone?
Because female is very constant.
Uh-huh.
There's no variation between kind of
Yes. So female variable 1, 1, 1. We happen to have no shifts in the gender identification, right? So if you aggregate the data, then you would have 1 as your average, right? And then you subtract the average, right? If they become all 0. And that would happen. The same thing would happen for all panels. As a result, the new female variable is all zeros for all people and for all observations. So therefore, there is nothing to explain it with, explain the y with. So it will be omitted. All right. Any questions? Nope. All right. And then so that's why if you're interested in the gender's effect on the depression scale, you should not use fixed effects models because it will be omitted. It will be gone away. And if you were to interpret close friends coefficient, you should say unit increase in the number of close friends over time within a panel is associated with 0.011 decrease in the depression scale over time within the panel. Does that make sense? So now that you subtracted all the panel-specific intercepts or means, you have to have, you should interpret the coefficients accordingly. All right.
So how we interpret close friend the coefficient is the same in fixed effect and relative.
So I'll cover that in the random effects models. But in the random effects models, the coefficient interpretation will be same as OLS regression models, actually. But for the fixed effects models, it is not, right? Because you're only looking at unit increase in close friends over time within the panel. Does that make sense? Yeah. All right. And then you can, the R square means the same thing. It will be slightly different because the coefficients are different, but we will not cover that for now. So there are different ways to look at why like the evidence to use fixed effects models versus pooled OLS regression. in this community. Actually. So again, this is FYI. This is not coming. So far we have covered the stuff that appears in the problem set or the exam. But let's move on to the FYI stuff. So the last line, F-test results, is based on the null hypothesis. It's a hypothesis testing result where the null hypothesis there is no panel specific intercept differences. Okay. So all the panel specific intercepts are explained away. Okay. And the results here suggest that the p-value is less than 5%, meaning that there are some remaining errors, intercept differences, even after you run the model. Okay. I mean, some of the panel-specific means in the regression scales can be explained with the certain regressors, right? Some people have closer friends for all time points or stuff like that. But even after that, you have this one, meaning that it's really good to have fixed difference models over pooled OS model. Okay. And then the second one here is correlation between the UI and XB. This is actually showing more of a giving the suggestive evidence of whether you should use fixed effects model over random effects models, actually. The last line was about fixed effects versus pooled OS, but so, for example, even though there are predicted values of y, right? Right, 2 predicted values. But as xb, the predicted value of y, this is xb, right? Increases, let's say ui is positive, and let's say this is u1, and this is u2. Oh, sorry, u1 and u2. This is negative, and this is positive, right? So it means that there's positive correlation between xb and ui. As the predicted value goes up, ui goes up. Does that make sense? Yeah. All right. So it really means that there is a variable u that affects x and y as well, that are time constant. I'll explain why. So, as x increases, the predicted value increased, right? But if the time, if this is a result of a confounder, it means that as ui increases, xi increases, xit increases, and yit increases. And that's why predictive value of y went up. And if there are also causal relationship from ui to yit that is positive, then precisely because you increased u to increase x and y, that means that there's another direct effect, correct? Another direct positive effect, and that'll increase the error level up. Does that make sense? Any questions? Am I making any sense? Again, this is FYI. Isn't covered in the problem set or exam, but I think it's useful to know.
So any of the two variables.
Oh, what?
So any of the two variables are positive correlated.
They're all positively correlated. Let's say that. So if u is a confounder, right? U increases, x increases, and y increases as a result, right? And if u increased and x increases accordingly, right? And therefore y is increased. But we are forgetting this path as well. This path independently affects y. And therefore, this one increases the expected value of u2, the estimated error. Does that make sense? Sort of? All right. And therefore, that's the reason, that's the suggestive evidence you can look at to see whether these time constant variables are confounders of the relationship between x and y. All right. Okay. And then I demonstrated how the fixed effects model does what they do here with the demeaning approach right there. So I basically run a demean data OLS. I run an OLS regression with the demeaned data. And then as you can see, the coefficients are exactly the same for close friend. And for SAM satisfaction, the coefficients are exactly the same. Right? Although the standard errors can be a little bit different because of the degrees of freedom. All right. So in terms of beta coefficients, the FV XT-reg command and demeaning approach agree with each other, but they don't in terms of standard errors, because what XT-reg does here is basically adding panel dummies in the model. OLS model. That's what XT-reg does. That A-reg command results are exactly same as XT-reg results. All right. As you can see right there, some 0.00, this one, they're same. So XT-reg and A-reg, they do agree with each other on that, any aspect. And let's I have to correct there is a mistake in that array command in the do file. So I'll upload the correct version, but the results should be same actually. But anyways. Now let's look at two-way fixed effects models. You can simply add time indicators. Time, which means you're adding I dot wave in the regression model. So that's how you can estimate two-way fixed effects models. Simply adding time domains. Good. Any questions? No? All right. And then you can also add cluster robust data error option even after you run a two-way fixed effects model. Right? As we saw in the lecture on Thursday, even after two-way fixed effects models, there could be some serial correlation among errors, right? As a result, you want to deal with this situation with by this clustering standard error, clustering errors. There are other approaches actually, but for that approaches, for these approaches, I recommend taking an HLN course actually. Third, let's look at random effects model. Oops. The results are pretty look same, except that there is correlation between UI and X fixed to 0. It's assumed. So random effects model assume there is no confounders, panel level confounder for the causal relationship between a time varying variable and the outcome. Does that make sense? Which is different from fixed effects, right? Does that make sense? No? So for fixed effects models, you are fixing all of the panel specific differences, right? And that's why you don't have to assume that there's no, so you are fixing all of the intercepts, right? In fixed effects models, right? And that's why you don't have to assume anything with the correlation between XIT and UI. Right? But in random effects framework, you have to assume that there are 0. The correlation between UI and X is 0. That's what it means. You don't control for beta 0 alpha. Good. And there is partial demeaning approach to the estimation of random effects model. I won't cover that in the section today, but if you have any questions about it, let me know. But it's simply letting you know how partial demeaning approach works in random effects model. And let's compare the results. As you can see, the first one is pooled OLS regression results. And the second one is between effects model, and the third one is fixed effects models, and the fourth one is random effects models. Right? So, yeah. So, as you can see in the fixed effects models, female variable is omitted. And what you can notice here is that the standard errors in between effects are largest, mostly, because you aggregate all of the data, and therefore you deleted out, disregard a lot of between variances, or all the within variances, right? And the sample size decreased from 6,000 something to 2,000 something. And that means that you are throwing a lot of information. And that's why standard errors are larger, because you yield less precise estimates. All right. And then lastly, let's talk about Hausman test. Hausman test is basically is about whether you should use a fixed effects model or a random effects model. It's basically comparing the coefficients of the two models. If they are too different, then you should use fixed effects models, because there's gotta be some confounding relationships going on from panel specific variables, right? If this is strong, this confounding relationship is strong, fixed effects coefficients will be a lot different from random effects coefficients, right? But if there is no relationship here, then coefficient won't be that different. Good? Yeah. The results suggest that the p-value is 0.7, meaning that there's not significant differences between the two coefficients, or the coefficients from the two models. In that case, I would use random effects model for efficiency, for the sake of efficiency. If the Hausman test rejects the null, then I would use fixed effects models. Good. Any questions? All right. So before you go, I really think that this is really important. These panel models are really important for your masters if you're interested in using these models for your masters. If you're a quantitative researcher, it's you have a high chance to use one of these models actually. So to demonstrate that, not demonstrate that, but give you an example of that. A bit embarrassing, but this is my masters, and I'll give you an example with that. So the setting here is y variable, some financial measure or something. But what I do look at here is the interaction between the variable called big 4 and then Rubin's cube, which is time constant for this one, time constant, and then this is time varying. Right? So the setting here is that the data had this structure actually. So each time point is nested within a firm, and a firm is nested within a business group. All right? So the data have 3-level structures. And then for the default model, I disregarded the business group component for good reasons actually. But for the 2-level model, I used the panel models with the 2 levels structures. Okay. So time points nested within each firm. Right? And then the big 4 means whether the firm belongs to big four business groups in Korea. So there is like there's a lot of business groups, and then they typically the four largest groups are called as a big four actually. And then they're time constant because they're belonging to the groups or don't change over time. And then Tobin's Q is a sort of financial measure that varies over time. Okay. And then let's look at so the results are summarized as this graph, but I also presented tables. The first one is fixed effects models, actually. So I wanted to look at, can you see that from back there, sort of? Okay, I'll explain what's going on there. So you can see that, right? Yeah. So to explain the y variable right there, I had Tobin's Q, which is time varying, and then I interacted with big four. Okay. And as you can see in these fixed effects models, there is no main term in the of big four here because it is time constant variable. It is omitted from the estimation results because it's a fixed effects model. Does that make sense? So if you're interested in main terms or plain terms effect on y, then you should not use fixed effects models. But I was interested in the interaction effect. So the interaction effect can change over time, right? Because it changes over time, and if you multiply the two variables, then it varies over time, right? So note that there is a subscript t-1 because I lagged the variables, meaning that to analyze the outcome of y at t, I used the variable 1 year prior because that makes sense in the causality from the causality perspective. All right. So that's the baseline model, and then I divided the sample to big four groups and non-big four groups, and run the same model by the groups. It was subgroup analyses. And the second analysis was random effects model because I ran the model because to have this one, big four variable. So now that it's not omitted in the estimation results, right? And I divide the sample and then ran the models. And then as a robustness check or something, from the baseline model, I added one more control variable that is lag dependent variable. This one. To really control for a certain latent propensity to have higher y. In that way, you will have much more confidence in the causal argument by controlling for latent propensity to have higher y. And lastly, I ran a multi-level analysis to account for three-level multi-level analysis, to be exact, to account for possible serial correlation coming from business groups. Right? So I ran a three-level HLM, and as you can see right there, ICC at the business group level is really low. It's less than 5%. Does that make sense? Yeah. So I can safely I mean, it's a robustness check, so to demonstrate like the ICC is really low, so that's why I chose the baseline model as these two-level HLM. Because ICC at the business group level is really low, right? But just as a robustness check, I added this one and let them know, oh, this is really low, so I don't have to care about it. Does that make sense? Yeah. Lastly, I did not use random slopes model, but used random intercepts model. Oops. Because it's in the HLM do file, so in the state of practice. But I ran the random intercepts model and random slopes model, and then I basically ran a log likelihood ratio test where you calculate the state of spits out log likelihood, something called the log likelihood, which really is about model fit to the data in a way. And then I do the same thing with the random slopes model, right? And then compare the two things. And if this one is random slopes model fits the model the data better, then I would use this one, right? But the p-values from the test suggest that it does not necessarily fits the data better. So that's why I ended up with this random intercepts models. And then the log likelihood ratio here is a log likelihood ratio test between OLS regression model. And then it has log likelihood of OLS, right? Okay. All right. Any questions about the panel models? All right.
So the straight up comment that we are doing today
Uh-huh.
is that you can use X set for the string level.
For three-level models, you should use mixed HLM. All right. So if you don't have any questions, yep. If you don't have any questions, I'll see you in the lecture tomorrow.
Literally.
개인 스코어 하는 거는 에그 아웃
개인 스코어가
트레이드 y 빼기 y
I feel confident, whether or not I understand.
보통 코델리카 CID랑 하니까
At this point, I feel like,
There you go.
First difference.
이게 first difference 그 다음에 이게 이런 이게 더
let me get some feedback.
one way fixed
Or- Oh, okay. Oh, tell me more.
근데 그 컨트롤이 동사 컨트롤이
Also, how about that?
그걸 맞춰준다는 말이잖아요. 그러니까 컨트롤 레그를 전문도치 아웃컴을 컨트롤했다는 말은 이 갭을 없애준다는 말이에요.
아예 없애주는 거는 이게 리니어하게 없애주는 거죠. 그러니까 리니어한 폭을 가정을 하고 거기서 나오는 것만 없애주는
Thank you. Send us out on our card. So that feels like, oh, we don't know. Why does it feel like it's right?
완전히 같게 만든다고 볼 수도 있지만 리니어 폭을 가정하고 만든다.
그러니까 이게 하면은 얘들은 원래는 이제 이런 거 이렇게 보면 시작 대비 똑같아야 되는 거
그게 이거는
컨트롤
완전 인색 매칭 같은 게
No, they need to pay
리니어
you.
컨트롤이라는 거는 리니어 폭을 가정하고 어느 정도 비슷하게 만든다는 거를 가정 완전 똑같은 게 아니라 정확하게는 아니에요.
컨트롤링 데피니션 자체가
그러니까 컨트롤이라는 게 둘이 크게 만든다는 거예요.
그래서
근데 이게 약간 이게 목적인 거예요. 정확하게. 리니어 컨트롤이 그거를 결정하는 그러면 리니어 그러다 보면
Remember how you're like, oh, there's another.
개념상은 그거랑 비슷한 거네.
네네네 비슷한 건데 살짝 그 개그를 그려보면은 개그를 그리고 조금 이제 뉘앙스가 달라지는 그러더라고요. 그래서
선생님 아까 여기서 선생님 그 페이퍼에서는 레그를 컨트롤했고
네네네
근데 그거를 개인 스컬처로 y를 빼고 하면은
근데 이거는 개인 스코어는 Y를 픽스 에펙트랑 레그드 아웃컴을 다 같이 넣었잖아요. 저는 둘 다 넣었잖아요. 그렇다는 거는 네, 둘 다 넣었다는 건 이거는 위딘 체인지를 보는 건데 그러니까 시간에 따라 어떻게 변하는지 보는 건데 그 위딘 체인지도 그 위딘 체인지에도 그러니까 이 프라이어 아웃컴이 위딘 체인지 자체에도 영향을 줄 수 있다라고 보시면 이해되시나요?
그렇죠. 네. 됐어요. 저도 비싼 거 좀 하려고 하고 있어요.
아, 네.
감사합니다. 네.
So,
可是我觉得你蛮聪明的。我真的考试搞很烂，搞得大家平均。没有，因为我听了之后，可是我是那种不会考试的，我不错的话，我就会忘记今天说。然后我觉得连扣的都很棒，都考不
right, because so the reason why I run from that and then I got the license, right?
这这么后面你在干嘛？
Yeah.
你是睡过头？
Yeah. So oh yeah. So if you run the model, you'll see the output in the last line. This one right here. So this really indicates the significant results that you should use HLM over just OLS. This, yeah, OLS versus HLM.
So is this one mentioned last time, it's outside the bound? Why you?
Yeah. This is the p-value.
Oh, so this is p-value, just reported on.
I guess so.
So this is about like.
Yeah, I assume so. Yeah, I think they should have done a better job in reporting this. But yeah, anyways, yeah. I mean, you could like said, oh, there's no p-value represents a significant of chi-square test for performance, which is chi-square test. So that's why it's yeah, that's one thing. Yeah, there's no okay. So I guess they did a good job.
Like their tables can be generated by
Yeah. So yeah. By looking at the outputs, you can just simply type in numbers. Significant less than 5%, then you should use HL or what else. Low. Yeah, for ICC it can be subjective, but so you can see both ICC for subjective judgment and for significance test you can use this one. They're talking about the same thing, but it is more of a this one is more testing rather than this is more of a subjective. Yeah. No, there's no like simple protocol, so I would say.
So for me, this one is easier.
That's true, but then you should also report ICC as well, which is reported in the paper as well, right? That one is ICC. No, that one. Yeah, that one is ICC. Depends. Oh, I would say this is. Yeah, this is really low. This is percentage, right? Oh, this means that really low.
Even this,
Yeah. Sure.
and it's consistent.
Yeah, I would use OLS if that's the case. Yeah. Yeah, this is consistent with the p-value.
Low ICC and significant.
Yes.
Some sign class you put notes on.
Oh, I sorry.
Problems that
Oh, yeah, sure. When do you want to?
I made a plan.
Oh, okay, sure. Yeah, then I'll see you on Wednesday.
I have a question.
Sure.
The code doesn't work.
Okay.
Like this. I just run it, but I don't know why this SD graph.
So you should install the package first. That's what I was saying. So there was a comment that this one, it was commented out, but you can simply copy and paste it to install.
And also the last one.
Yep, and that's that. Yeah,
I
you can
also,
do that same thing with that as well.
so I need to also need to install this.
Yep.
This package.
Mhm.
Another quick question.
Sure.
Like, I didn't see this part. What is the hypothesis here?
Oh, what?
Like F tags like this.
Oh, so it means that you should use the p-value being significant.
Yeah.
means that you should use fixed effects model over OLS.
So the null hypothesis.
Fixed effects models and OLS results with the data same.
This
Effects models
model.
and OLS model fit the data to a certain to the same degree.
So you reject it, so it means that
You should use fixed effects models.
this part is
Yeah,
for fixed
that
effect,
one.
and we rejected this means reject the fixed effect.
Reject the null hypothesis that they yield the same results. So that's why you should use fixed effects models.
Oh.
Yeah. Mhm.